Okay, this is our second video that's associated with the PowerPoint slideshow called Equilibrium Part 3. Oh, sorry, that was our paper from the first video. And this is really a huge important learning outcome for our course. RICE tables or ICE tables are also called. Either way, this is really important. We're going to use it on almost every single exam. It's going to be all over the final, so please take some time, spend some time in this content. It's really important. Okay, so we know how to tell if a reaction is at equilibrium by plugging in the values, concentrations or pressures, into the K expression. Beep, boop, boop. Using our calculator, do we get the numerical value of K, the equilibrium constant? If the answer is no, it means we're not at equilibrium. This type of problem, a RICE table or ICE table, it allows us to calculate or allows calculation of equilibrium amounts given initial amounts. Because we know mathematically what that equilibrium constant expression must equal, we can use a system called an ICE table or a RICE table. And we're going to start with the type of problem where in the problem we're only told how much reactant or reactants we are starting with. So a RICE or ICE is for reaction I is for initial. That's what we start with, right? That's what initial, beginning, means. C is for change. Change in concentration, change in moles, change in pressure. And then E is for equilibrium. This is the line that we will plug into the K expression. This line, these either equations or numbers, these values are plugged in the K expression. Sorry, I'm running out of room a little bit there. But we have to get to that line using all these other pieces. So let's see what that looks like. In the slide, we have a reaction. We've got N2O4. It's a decomposition reaction breaking down into 2NO2. Okay. We're given a value of K, that's also really important, and we're given the initial concentration. So the reaction is just my balanced reaction, and then under that, my initial line is any initial amount or starting amount. So I'm looking for those words initial or starting, or two concentrations are placed, or this amount of moles are placed in a container. You know, that's something that indicates the beginning. And this is 0.25 molar. Because I'm not told in the problem, oh, you also have this amount of nitrogen dioxide, I can safely assume I don't have any of that to start with. If I'm not told in the problem that I have an amount of something, I don't start with any. Okay, so that's it. That's my initial line. I get that information from the problem. My next line is the change. This one is pretty straightforward. It can get tricky, but this means one side is losing and the other is gaining. The atoms, the nitrogen atoms in this product come from breaking apart this nitrogen-containing compound. So I have to lose some amount of my reactant in order to reassemble the atoms to form the product. I'm losing from this side. How do I know that my negative sign is on that side and my positive is on my product side? Well, I can't take away from 0. If I don't have any molecules of, let's say this image is is a nitrogen, an open circle, and 2 filled circles are the oxygen atoms attached. Let's say that, which is totally not the structure, but let's say that's what it looks like. If I don't have any of these, I don't have any nitrogen atoms or oxygen atoms, I don't have anything to form more reactant. I can't subtract from 0. So when I'm only given either reactants or only products to start with, then I know my negative is on the side with some amount I've started with, right? So negative from my reactant side because I was given an initial amount of reactant and 0 product. The signs will always be opposite as we cross that equilibrium arrow. We're always going to have a different sign. Okay, now how do we know what to put next to those signs? We put the coefficient, so that's an understood 1 for N2O4 and a 2 for NO2, and then I'm just going to put a variable. I use X. That's, I think, one of the toughest steps. The last step I think is pretty easy. That's the change. Equilibrium is just the initial and change lines combined. So it's just 0.25 minus X, and then on my product side, it is 2X. Remember I said the equilibrium values are what gets plugged into the K expression. So if I have a K value, and in the problem it's given as 2.00, I can then plug in these values into my equilibrium constant expression. Remember, I set that up with products over reactants, no solids, no liquids. Any coefficient becomes an exponent. What you'll notice is we will have that coefficient inside the bracket as part of the equilibrium expression line, and we'll have that same number as an exponent. So we will see the coefficient in 2 different places when we solve these types of problems. Okay, so then we get into some fun algebra, and I think that's on our next slide. Okay, so this is how we set it up. We set up a RICE table reaction, any initial amounts. If something isn't told explicitly in the problem that you're starting with some of that, then we don't have any. When you're starting with only reactants, in your change line, the negative has to go under your reactants and the positive has to go under your products. You have to form some products because you don't have any yet. You drag down any coefficient and then write the letter X, the variable X, or any one you want. I always use X. Finally, the equilibrium line is just combining those two together. I'm not changing any signs. I'm effectively adding initial and change together. Okay. Once we set up the ICE or RICE table, I set up the equilibrium constant expression, and then I substitute the molecules that I start with. I substitute that with whatever's on the E or equilibrium line straight underneath that particular molecule in the expression. Okay, I set it equal to the value of K that's given in the problem. Occasionally you'll have sort of a twist where you're asked to find K. Well, that means you're given one of the equilibrium concentrations. We'll do a problem like that in a few videos. Okay, so let's get started with everyone's favorite algebra. So I'm going to multiply both sides by this term, 0.25 minus x. All right, so I have 2 times 0.25 minus x, those are in parentheses, equals 4x squared. So I do have to make sure that I am squaring both the 2 and the x. And then 2 times 0.25 is 0.5 minus 2x. So I distribute those terms. Oh man, quadratic time. Okay, so how do I do the quadratic? Well, I have to get everything to one side because it's ax squared plus bx plus c equals 0. So I have to subtract everything to the other side. I'm going to use a different color or add. So plus 2x. And then I'm going to subtract the 0.5 to move that over. And that leaves 0 on one side of the equation and an x squared term, an x term, and then just a numerical value or constant. If you're in calculus, you'd call this the constant term. Okay, back to the quadratic. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. You can program your calculator to do this. I'm not really concerned about testing your algebra skills. I don't usually give a problem where you have to use the quadratic. I usually have some kind of shortcut in there that we'll talk about later. But you might see some of this. You'll definitely see it on your homework, and you need to know how to solve this type of problem. Okay, so a equals 4, b equals 2, and c equals negative 0.5. All right. So x equals the opposite of b, which is negative 2, plus or minus the square root of b squared, which is 4, minus 4 times a, which is 4, times c, which is negative 0.5, all over 2 times a, which again is 4. All right, negative 2 plus or minus the square root of 4 minus plus, minus a negative is a plus. 4 times 4 is 16, times a half is 8, divided by 2 times 4, which is 8. Okay, so that's what I'm getting so far. I'm going to get 2 different values for x. One's going to make sense and the other one just will not make sense. So let's see what we get. 4 plus 8 is 12. So this is negative 2 plus the square root of 12 over 8. I'm going to call that x1. Or x2 would be negative 2 minus the square root of 12 over 8. Okay, well, x isn't going to be a negative number. X is what the change is. So x has to be a positive number. I'm just writing that down. X must be positive. Okay, so this one won't make sense because a negative number minus a negative number divided by a positive number is always going to be negative. So I can get rid of what I'm calling x2. Okay, so that means my number should be negative 2 plus the square root of 12 divided by 8. I'm going to pop over to my scientific calculator. Okay, so negative 2 plus the square root of 12. Oh, that's a minus. Negative 2 plus the square, there we go, square root of 12. I'm going to hit enter, and then I'll divide by 8. I need to use parentheses if I'm trying to do that in one step. So negative 2 plus the square root of 12, I got about 1.46. And then divide by 8, I got 0.183. So how do I check my answer? Here's what's really awesome about this type of problem. You plug it back in, and if you get the number K back, then you know you did it right. Don't you love problems that you can always check to make sure you're doing it right? Especially on an exam. You know what I'm talking about. Okay, so what does this mean? Is this my answer? No. I'm asked, what are the equilibrium concentrations? The equilibrium concentration of N2O4, I'm going to write a little EQ as a subscript, meaning at equilibrium, and the brackets mean specifically molarity. This is equal to whatever I wrote on that line. In this reaction, it's 0.25 minus x. Well, I solve for x. So what do? I just plug in x. So 0.25 minus 0.183. Listen, if I get a change, an x value that's bigger than what I start with, that's a clue that I made a mistake, right? I can't lose more than I start with. I can't have 5 moles of something and convert 6 moles to product. I don't have 6 moles. I only have 5. So that is a big clue. And this one I think is 0.067. Is that right? 0.25, that's 0.7. I think so, but I'm going to double check. Oh, I haven't had my coffee in several hours, so I'm not really reliable. 0.25, whoa, really did not like that. 0.25 minus, oh, I don't have the number lock on. Why would you ever take off the number lock? Anyway, yeah, 0.067. Just wanted to verify. Okay, so this is one of my answers. The equilibrium concentration of N2O4 equals 0.067 molar. Okay, that's one of the numbers I'm going to plug back in to check my answers. But I also need the equilibrium concentration of NO2. And if I go back up to my ICE table and I look at that equilibrium line and the entry that's straight down below NO2, it's 2x. Exactly what is in the line. So I'm going to plug in 2 times 0.183. I don't have a square here. The only time I have a square is in my equilibrium constant expression. Oh, where did you go? Here we go. I only have the square in this relationship with the numerical value of K. The square isn't the concentration. What's inside the brackets is the concentration. What's in that block, in that equilibrium line, that's my concentration. The square is just there to make it equal to K when I put all those things together. Okay, and 2 times 0.183. There we go. 0.366. Okay, so now I have what I believe are the equilibrium concentrations. Now, how do I check? Let's go back. Let me go back to my visualizer screen. How do I check? Well, if I plug these values in to the equilibrium constant expression, I need to get that number back. Okay, so I'm going to write Kc equals 2. That's what I need to prove. I can put a little question mark there. And then I have to look. The top term is NO2, which is 0.366 entire quantity squared. On the denominator, I have what I solved for earlier, which is 0.067. That's the equilibrium concentration of my reactant, the dinitrogen tetraoxide. Okay, so let's plug this in to the calculator. 0.366 squared divided by 0.067. Okay, I get 1.999 and a few more digits, and I am definitely comfortable with that because I did round these values just a little bit. So I'm going to put a check mark there. I got 1.999, so I am good. I am all set there. So that's one way to check your math, to make sure you did your math correctly. Okay, so that's how to solve with a RICE table when you're given some initial amount of reactant, no product to start with.